This is our second lecture of Chapter 15, which deals with stereochemistry. So in this presentation, we will cover the following. First, we'll do a review of the concepts of chirality and enantiomers. You may recall these are new terms that we learned in our last lecture. So we'll do a quick review of these terms and the applications and importance of these concepts. Next, we will look at the nomenclature of enantiomers. Remember, we emphasized or pointed out that enantiomers are different molecules, different stereoisomers, so they must have different names. Next, we'll look at the physical property of enantiomers. Notice I'm not indicating here properties, but just one. There's only one property difference between the stereoisomers known as enantiomers. Lastly, we'll do a summary and show the importance of chirality or stereochemistry in biomolecules. So once again, I just wanted to remind everyone that this concept here of stereochemistry and analyzing molecules in three-dimensional space requires a lot of visualization. So I strongly recommend, if you can get a hold of a model set, to do so and build your models as you read along and watch these videos. It will really help you grasp the analysis of three-dimensional thinking. So let's begin. So as a quick review first, you may recall chirality. Objects that are non-superimposable on the mirror image are called chiral molecules. So once again, these are two different stereoisomers, to be more specific. Stereoisomers, remember stereo means orientation in three-dimensional space. So these are stereoisomers, and if they are non-superimposable on each other, they are called chiral molecules. The common feature of chiral molecules is that there is a carbon that has 4 different groups bonded to that carbon. So chiral molecules have 4 different groups bonded to at least one carbon in the molecule. We say that that carbon is a stereocenter. So if you can find the stereocenter for the stereogenic molecule, you know that you have a molecule that its mirror image is non-superimposable on itself. A lot of new terms here, and that's the way chemists, especially organic chemists and scientists, communicate with these terminologies. So make sure you understand what they mean so that you can effectively communicate and understand and apply these concepts. Another term is achiral. As you can imagine, the A means here the opposite of chiral. So it's without chirality. So the mirror images here are in fact superimposable on itself, which means that they are the same. Enantiomers is another term that we introduced. And remember that enantiomers are non-superimposable mirror images of molecules or of stereoisomers. So they're called enantiomers. Don't forget that term. And of course, lastly, we concluded that enantiomers always come in pairs, only two, because they are mirror images of each other. And the comparison we used was that of our hands. We have a right hand and a left hand. They are mirror images of each other, and they are different. Okay, so let's look here at two molecules. So these two molecules that are shown below. Let us do our analysis of these two molecules. First, notice that they have the same chemical formula. Okay, so in other words, they will be isomers of each other if they have the same chemical formulas, depending on the arrangement of the groups there. Another important observation is that there is a carbon with 4 different groups. So once again, I should remind you, and as you go through organic chemistry and becoming a better scientist, one important aspect is the ability to make observations. We make conclusions based on observations. So here is an important observation about these molecules. There is a carbon with 4 different groups. Here is that carbon right here. It has an OH, it has a methyl, CH3, it has a hydrogen, and it has an ethyl, CH2CH3. So there are 4 different groups bonded to this carbon. So therefore that carbon is described as a stereogenic carbon. Let's look at the other molecule. It also has 4 different groups: OH, CH3, C2H5, and a hydrogen. So this is the stereogenic carbon. I should point out that another important observation is that these 4 groups in the top molecule here are the same in the bottom molecule. So therefore these are isomers. Specifically, they are stereoisomers because the connectivity to the atoms are the same. The only difference is the arrangement in space. Notice this hydrogen is in front, and here it's in the back, as indicated with this dash. The dash means that it's in the back, and the wedge means that it's in the front. So that's again another concept that we introduced earlier to indicate the location of atoms in a molecule as drawn on a piece of paper, which is 2D. The dash and the wedge to indicate front and back. So these two molecules are stereoisomers. So the question now is, are they superimposable on itself? We indicated and showed the last time that it's possible to visually take these molecules up and orient them, and if they are superimposable, they are the same. If they're non-superimposable, they are different, and there's a special name for that difference, and that's enantiomers. So if you are good at visualization, you will see that these molecules are non-superimposable on itself. Therefore, they are different molecules. And if they are different molecules, the relationship is that they are enantiomers. So again, this is a very difficult concept to visualize because we're looking at these molecules in 3D, plus we have to manipulate them in 3D. But let us see if we can find an easier way to determine if these two molecules here are the same or are they different without visualizing them in 3D and manipulating them to see if they are superimposable or not. So let us look at what three chemists did years ago, Kahn, Ingold, and Prelog. They came up with a system of naming the molecules, that naming enantiomers. They call it the R and S assignment of absolute configuration. So mainly R and S. And notice it's just two, R or S, because as we said, enantiomers come in pairs, just two possibilities. So let's see if we can look at these rules that they devised to determine if molecules are R or are they S. So the first step in determining if a molecule is R or S is to arrange the groups that are bonded to the stereogenic center based on atomic number. Okay, so we got to look at each atom that's bonded to the stereo center and determine the atomic number and arrange them in terms of priorities. So let's look at the next slide to apply that and see what that really means. So if we have this molecule here, 1 bromo, 1 chloroethane. So here is the chiral carbon, or the stereogenic carbon. So we'll have to look at the 4 groups that are bonded to it. Here's 1, here's 2, here's 3, and here's a 4th group. What the R and S rules state is that we'll have to assign priority based on atomic number. So you will need your periodic table here. So here's a chiral carbon, here is a bromine, a chlorine, and a carbon, and a hydrogen that's attached here. So which of these 4 atoms has the highest atomic number? Looking at your periodic table, you will see that it is bromine, because bromine here has an atomic number here of 35. So this gets number 1. Chlorine has an atomic number of 17, so it gets number 2. Carbon has an atomic number here of 6, so it gets number 3. Hydrogen, as you know, has an atomic number of 1, so it gets number 4. So once again, we assign priorities of the atoms that are directly bonded to this chiral center based on the atomic number. So we do that assignment. So we're looking at 2 molecules here, which will decide if they are the same or are they different based on the R and S absolute assignment. So let's do the same here. Bromine has an atomic number, as we said earlier, of 35. Chlorine has 17, so it gets number 2. Carbon has atomic number of 6, so it gets number 3. And hydrogen has the lowest atomic number, so it gets a priority of 4. There's only a possibility of 1 through 4. So once you have prioritized these atoms or these groups that are bonded to the chiral center, let's see what we do next. Next, you'll have to orientate the molecule so the group of lowest priority is in the back. That's where the dash and the wedge will become very important. And then you trace the numbers going from 1 to 3. If the direction is clockwise, it's an R. I remember here a clock is, we're talking about from the old school clock, where it's not digital clocks. It's where you have 1 through 12 in a circle, and the minute hand goes clockwise or counterclockwise. So 1, 2, 3, if it's clockwise, it's an R, and if it's counterclockwise or opposite, it's an S. So let's see what that means. So here's an example. This is not the clock, but it's a steering wheel, for example, but same concept. So if you go 1, 2, and 3, it's an R. Notice that the 4 is in the back or away from here. So once again, trace the numbers. 1, 2, and 3, it's R. As you can imagine, if it goes the opposite direction, it will be an S. And there's an example next. So let's apply this concept here. So, looking at the same 2 molecules, we have 1, 2, and 3. Notice that the hydrogen here is in the back. So we need not concern ourselves about 4. We just go 1, 2, and 3. This direction here is clockwise, therefore it's an R. So the full IUPAC name of this molecule is now R1 bromo 1 chloroethane. Let's look at this other one. This is, hydrogen is again in the back, so we go 1, 2, and 3. This direction here is counterclockwise, so it gets an S. So the name of this molecule here is S1 bromo 1 chloroethane. Notice they are different because of the R and the S. Conclusion, these molecules are enantiomers. They are different. So again, this gives you an easy way or an easier way to determine if 2 molecules are the same, which means they are superimposable, or different, which means they are non-superimposable and hence enantiomers, by determining the absolute configuration, or the R and S absolute configuration of enantiomers. Let's look at another example here. So you may be asking, what if the group of lowest priority is not in the back? So we have a comparison here. So notice for this molecule, as drawn, the group of lowest priority 4 is in the back. Because why? Because of the dash line. Over here though, the group of lowest priority is not in the back, it's in the front. How do we know that? Because of the wedge. Because of the wedge. So based on the rules, we trace 1, 2, 3. This is an S because it is going counterclockwise. So this molecule is S1 bromo 1 chloromethane. On the other hand, however, we still can trace 1, 2, 3, but because this group is in the front, it's going to be the opposite. So let me emphasize, the only reason why this is looking like it should be an R, but not an R assignment, is because the group of lowest priority here is in the front. So again, you have to be very observant to determine if the group of lowest priority, number 4, is it in the back or is it in the front? Conclusion, after we've done the observations And after we have done our analysis, our conclusion is that these two molecules are the same. Why? Because they have the same name, S and S, or should I say the same absolute assignment, S and S. Okay, so let's apply that to another example here. The question now is, can we assign absolute configuration of R or S to these molecules? And again, one of the importance here is once you have assigned R or S, another terminology is absolute configuration, you can determine if the another stereoisomer which has the same groups connected to it, are they the same or are they different? So let's see how we assign R or S to these molecules. Here is the carbon. It is the stereogenic center because it has 4 different groups bonded to it: OH, CH3, C2H5, and H. Then we'll have to look at the atomic number of the atom that's directly bonded here. This is oxygen, so look at your periodic table, determine the atomic number of oxygen. You'll see that it's 8. This is carbon, look at your periodic table, determine the atomic number, and you will see that it's 6. Look at this one, this is carbon, look at your periodic table, you'll see that it's 6. So we'll have to make a decision between this carbon and this carbon. In that case, we go to the next atom. The next atom here is carbon, which is 6. The next atom here is hydrogen. So this will have priority over this one. And of course, here is hydrogen. It has an atomic number of 1, so therefore it has the lowest priority. An important observation is that this is in the back. So whenever you trace that, you will just make your conclusion based on, is the tracing from 1 through 3, is it clockwise or is it counterclockwise? Let's look at alanine. Chiral carbon right here, because it's bonded to 1, 2, 3, and 4 different groups. So let's analyze each separately again. Nitrogen. Look at your periodic table. It has an atomic number of 7. Carbon has an atomic number of 6. But here's carbon, atomic number of 6. So in this case, we go to the next atom, oxygen. The next atom here is hydrogen. So this gets a higher priority than this one, but not as high as this one because this is 7. And of course, here is hydrogen, the lowest priority, and again, it's in the back. So that is the observation. And again, I'm emphasizing this because as we are improving our scientific skills, I mentioned that an important aspect of our scientific development is observation. We have to take the time to make observations, and that's the only way we can make good conclusions, is making effective observations. So let's look at the next slide for the assignments. So as you can see here, this gets number 1 because the atomic number is higher than carbon and carbon. This gets number 2 because this is a carbon bonded to another carbon, and this is a carbon bonded to another hydrogen, or 3 hydrogen. So this gets number 2. This gets number 3 because it's next, and of course hydrogen gets number 4. Also important, it's in the back. You trace 1, 2, and 3. We get R. So the absolute configuration of this molecule is R, and its complete name now becomes R2-butanol. Let's look at alanine. This is nitrogen, atomic number 7. This is carbon, atomic number 6. So this gets higher priority. This is carbon atomic number 6. This is carbon atomic number 6. So we have to make a decision which one of these two gets the higher priority. We look at the next atom bonded to this one. It's a oxygen, which has an atomic number of what's that, 8. So therefore this gets the higher priority, number 2, and this gets number 3, and of course hydrogen gets number 4, and it's in the back. So when we trace this, we get clockwise R. So the absolute configuration is R, and the name of this molecule is R-alanine. So let us look at the natural occurring amino acid and the unnatural occurring amino acid. And the difference is the arrangement in space. So let's see if we can make the assignments. We know this is 1 because nitrogen has the highest atomic number of these 4 atoms. We know this is going to be 2 because this is a carbon which is bonded to an oxygen. We know this is going to be 3 because this is a carbon atomic number 6. And we know this is going to be 4 because it's hydrogen, the lowest atomic number of 1. So then we go 1, 2, and 3. So you can see this is counterclockwise, going against the direction of the minute hand on a clock. So therefore this is the S direction. So therefore this is S-alanine. Let's look at this one. Nitrogen again has an atomic number of 7, the highest of these atoms here. So this gets number 1, carbon and carbon, but this carbon is bonded to an oxygen, so it gets number 2. This is carbon bonded to hydrogen, it gets number 3. And lastly, this is hydrogen, which has the lowest atomic number, so it gets number 4 priority. In this case, we go 1, 2, and 3. So this would be the direction of tracing priority numbers. This is the direction of the minute hand on a clock. So this is the R, and this is R-alanine. So this is the natural occurring alanine, the unnatural one. This is the one that's used for building of peptides and biosynthesis of proteins, and this is not. We mentioned earlier that the body can recognize the simple difference between these two molecules. So once again, these two molecules are different. They are enantiomers. They are mirror images of each other, and they are different. They are enantiomers. Okay, let's see if we can do the priorities. I mentioned that you look at the atom that's directly bonded to the chiral center, but if there are 2 carbon atoms, how do we determine which has a higher priority? So let's look at these examples here. So just imagine here that this is the bond to the chiral center back here. So here's a chiral carbon, and here's a chiral carbon. So if these 2 groups were bonded to a chiral carbon, which of these 2 groups here would have the highest priority? So this is a carbon, and this is a carbon. So we can't tell. This carbon is bonded to an oxygen, however, and this carbon here is bonded to another carbon. So this would have the highest priority. Here's another example. So the chiral carbon would be back here. So this is a carbon. If the chiral carbon were back here, this is a carbon. Can't tell. But this carbon is bonded to another carbon, and this carbon here is bonded to a nitrogen. So we would expect that one. Here's another example. This carbon and this carbon, so they're both carbons bonded to a chiral center back here. But this carbon is bonded to a oxygen, and this carbon is bonded to a carbon. Since the atomic number of carbon is greater than the atomic number of, since the atomic number of oxygen is greater than the atomic number of carbon, this will have priority over this group. Let's look at a last example. So again, it's bonded to a chiral center back here, and here's a carbon. But if it's bonded to a carbon here, how do we determine which of these two groups will have higher priority? This carbon is bonded to a nitrogen, and this carbon is bonded to a carbon. Since the atomic number of nitrogen, I need to get that correct, since the atomic number of nitrogen is greater than that of carbon, this will have higher priority. So let's look at the answers. So as shown here, this has the higher priority because of this oxygen, and this carbon here is a lower priority. Same here, nitrogen makes this group the higher priority group compared to this group. This one here, oxygen, makes this group the higher priority compared to this group. And lastly, as we said, this nitrogen has a higher atomic number than carbon, so therefore this group has a higher priority compared to this group. So I guess the bottom line is, if you had these groups bonded to a carbon, 1, 2, 3, and 4, can you prioritize to see which one has the highest priority and the lowest priority? Granted, we won't get that complicated in this course. I'll just keep it as one atom that's bonded to the chiral carbon, so you can make a quick observation and a quick determination on priority and determine if the molecule is R or S. Let us look at an example I gave earlier in terms of ibuprofen. As we know, that's a painkiller, analgesic. So let's look at this again. Here's the molecule. Here is the chiral carbon. How do we know that? Because it has 4 different groups bonded to it. We know that its mirror image is different from the molecule because they are non-superimposable. The body can recognize the difference. So now we can assign R and S based on the R and S system of nomenclature or absolute assignment. So let's see if we can do this. This is the chiral center or the stereogenic center. A carbon is bonded to it, a carbon is bonded to it, and a carbon is bonded to it, and of course a hydrogen. So of these 3 groups that have carbons, which has the highest priority? Since this carbon is bonded to an oxygen, this gets number 1. Since this carbon is bonded to another carbon, and here even another carbon, notice carbon, not oxygen, it gets number 2. This carbon is bonded to hydrogen, so therefore it gets number 3. This of course is number 4, and it's in the back. Let me just emphasize here, back. So when you trace it, it's going in this direction, so therefore it's an R, and it's R ibuprofen. So okay, let's look at this other one. Same as analysis, chiral stereogenic center. This gets number 1 because of this oxygen. This gets number 2 because it's bonded to carbon. This carbon gets number 3 because it's bonded to hydrogen, and this is of course number 4. So when you trace this, you go in this direction. This is S, so this is S assignment, so this is S ibuprofen. Different molecules, different isomers, relationship enantiomers. The body can detect this difference, and as you can see here, this molecule here, R ibuprofen, is inactive. So if you had a headache and you ingested R ibuprofen, you would not be relieved of the headache. However, if you ingested the S ibuprofen, this one, that would be active and relieve you somewhat, well, relieve you of the headache. Okay, we're closing here, so let's look at a couple other concepts here. Most organic molecules, especially those in nature, they have more than one stereogenic center. So what we're asking here is, looking at a molecule that's drawn like this, or using the dashed wedge, can you quickly identify if it has a stereogenic center or not? And why are we doing this? Because a molecule that has a stereogenic center, we know that its mirror image will be different from the molecule. We call that relationship the enantiomers. So looking at this molecule, is it a molecule that has a stereogenic center? Or can we say, is it a stereogenic molecule or not? Looking at this, can we find it? So let's look at this one, for example. Here's a carbon. I'll circle this carbon. It's bonded to this group. It's bonded to an OH. It's bonded to a CH2, CH3, and a hydrogen. So this is a stereogenic center. So this molecule here is stereogenic. Let's look at this one. Let's look at this, for example. This carbon. Here's a methyl group CH3 and here's a methyl group CH3. These two are the same, so this is not a stereogenic center. Well, we have the answer on the next slide, so let's just do the analysis. Here is another molecule. Let's look at this carbon, for example. This carbon only has 1, 2, and 3 groups bonded to it, so this is not a stereogenic center because it only has 3 groups. Remember, for a stereogenic center there has to be 4, so therefore this is not only 3 groups. Let's look at this one. This is hydrogen. That's not shown because we're using the dash wedge. Since it has 2 hydrogens, this is not a stereogenic center. So let's look at the answer. So here, this is a stereogenic center, as we said. This is a stereogenic center because we have a hydrogen here. So we have 1, 2, and here is 3, and here is actually 4. Here is another stereogenic center because we have 4 groups, 1, 2, 3, and all of that is 4. Here's another center because we have hydrogen here, 1, 2, all of this is 3, and all of that now becomes 4. Here's a stereogenic center. Don't forget your hydrogen, 1, 2, 3, and all of this now is 4. Here's one, hydrogen again. Here's another one, hydrogen again. So we got 1, 2, 3, and 4. Same here, hydrogen. So 1, 2, 3. All of this back here going in this direction is 3, and going in that direction is 4. Same here. So again, you should be able to identify stereogenic centers on a molecule. Again, for emphasis, this is extremely important because the biological system or the body can recognize these and will use typically just one for biological activity. Okay, lastly, let's look at physical property. So as we mentioned here, enantiomers differ from each other in just one physical property. Let me remind us again, a physical property is an observable or measurable property of a molecule. Water, for example, is colorless. That's observable. It has a boiling point of 100 degrees. That's measurable. That's why water is different from ethanol, because the boiling points are different physical properties. Enantiomers, they have the same physical properties in terms of color, in terms of melting points, in terms of boiling points, except only one. Only one. Let's see what that is. So, well, I'll tell you and then we'll explain it. The only physical property that's different is in the direction in which it rotates the plane of polarized light. So again, that's a new concept, polarized light. So let's define light. So whenever light that's coming at you from the bulb or wherever you're getting that illumination, the waves are vibrating in all planes perpendicular from the initiation point. So it's all planes. Polarized light, however, is vibrating in only one plane that's parallel. One plane. So the difference is polarized light, all the other planes have been filtered out and it's projecting only in one plane. You may have seen on TV polarized lens. What that does is to filter all the light in different directions and you get polarized light coming through. A polarimeter is the instrument that's used to measure the degree of polarization of compounds. Here's another term for you, optically active, because enantiomers can interact with polarized light. We say that enantiomers are optically active. So that's another term that we'll use. Enantiomers are optically active. Enantiomers are optically active and they also contain stereogenic center. So we also describe them as stereogenic molecules. So these are all synonyms. Let's see how that works in terms of the property. So here's a polarimeter, the schematics for a polarimeter. So here's light. So that's just light coming at you. Here's the illustration of it being propagated in different directions. But once it passes through a filter, then it will be now vibrating in only one direction as shown here. That light now passes through a sample. If it's an optically active sample or one of the enantiomers, it will rotate the plane as shown here by a specific number, specific degree. So that means that the sample that's in here, if there's a rotation here, it is optically active and it is one of the enantiomers. I should point out here that if you should clean this vessel and put in the other enantiomer, it would rotate it in the opposite direction by the same degree. So let's apply that. So here is an organic molecule, lactic acid. If you should put this molecule in the polarimeter, in that sample chamber that I pointed out earlier in the previous slide, it will rotate the plane of light by 2.6 degrees. It will rotate it clockwise, and we assign a positive to it. So this is an experimental determination. Another term that's used here, let me not confuse you. Yes, so it is an experimental determination, so we give it a plus. Another term that we often give to it is an L or a D. So remember that sometimes you see amino acids as L amino acids and D amino acid. That is because it rotates the plane of polarized light in the clockwise direction or the counterclockwise direction. Notice that back in the day, it's always making reference to the clock, because that was, of course, an essential tool back in those days, and still today, but the clock was a little different. It's not the digital clock. It's a clock that's shown with the numbers and the minute and second hand going in the clockwise direction. So here's lactic acid, and it rotates the plane of polarized light by 2.6 plus. So that's why it's assigned a positive here. Here is its enantiomer. It will rotate the plane of polarized light by the same number, but in the counterclockwise direction, so it gets a negative, or it's assigned a negative. So again, this is an experimental determination. So if you're an experimentalist and you have synthesized a new compound in the lab, and you have determined that it's optically active, you can go in the lab and determine if it's a plus or a negative, and assign to it the physical property of optical activity. So let's conclude by looking at the importance in biomolecules. So as we have seen, that the living system can in fact distinguish between chiral molecules in terms of its enantiomers. So we can see here that most of the organic compounds that exist in nature exist as stereoisomers. And as we have pointed out, these are very important in the biological system. So let's conclude by looking at two important pharmaceutical compounds that we use on a regular basis: ibuprofen and naproxen, pain relievers. As we pointed earlier, the S ibuprofen is the one that's active, not the R. Here's one that's of extreme importance: naproxen, again a pain reliever. Notice it has a chiral center right here. So these centers here are not chiral or stereogenic, but right here. So therefore its mirror image is the enantiomer. But as you can see here, this enantiomer here, the S, is the one that's active as a pain reliever. Of importance, especially in the pharmaceutical industry, the R is a liver toxin. So whenever the pharmaceutical industry makes naproxen, they will have to make sure that there is no R contained in that pill or that tablet. So that's why you'll see on the ingredient it's 99.99% pure, because if it has any of the R, there will be extreme problems in the system, because it's a toxin or poison to the liver. So this is really a good example of the importance of enantiomers in chemistry and more specific for biomolecules. This is the end of chapter 15. So once again, please take your time and read through the chapter. Take your time and watch the video here. Hopefully I've done a good job to explain the concepts in this chapter of chirality and stereochemistry. You may have to pause at different times and get your model set and build your models. Just try and understand the concept. Again, as scientists and chemists, we're not just here to memorize the material and reproduce it. We're here to help to use this information to help us to become a better scientist, a better thinker, and to be a better problem solver. So continue to work hard, and I will have more information posted in D2L about what's coming up this week. We'll have an exam on Thursday. So continue to work hard at organic chemistry. Okay?